Good day to Doctor and my fellow friends. I'm Ivan and my teammate is Jing Hong. Today we are going to present our M1 experiment called resistivity measurement of semiconductors by 4-point probe method.
For this experiment, the apparatus used are the probe arrangement, germanium sample, oven, 4-probe setup, and thermometer. The germanium sample acts as the semiconductor material, while the oven is used to change the sample temperature. The 4-point probe method is used to measure semiconductor resistivity accurately. The two outer probes supply constant current, while the two inner probes measure voltage. This arrangement helps reduce contact resistance and leak resistance errors.
Now I will talk about procedure. The germanium sample was placed on the base plate and the 4 probes was gently positioned to ensure proper contact. The outer probes and inner probes were connected to the current supply and voltage terminals respectively. The setup was placed in the oven and the thermometers was fixed in position. The power supply was switched on and a constant current of 5 mA was set and the voltage across one probe was measured. The sample was heated and voltage readings were recorded with increasing temperature up to 140 degrees Celsius. The probe spacing and sample thickness were measured. The oven was switched off and voltage readings during cooling were recorded in the end.
For increasing temperature, the voltage generally decreased from 38.2 mV at 323 Kelvin to 4.6 mV at 430 Kelvin. Since the current is constant, this means the resistance and resistivity decrease when temperature increases. For decreasing temperature, the voltage generally increased from 6.8 mV at 430 Kelvin to 33.3 mV at 323 Kelvin. This shows the resistivity increased when the semiconductor cools down. For question 1, the advantage of the 4-point probe method is that it separates current supply and voltage measurement. The outer probes supply current, while the inner probes measure voltage. This reduces contact and leak resistance errors, give a more accurate resistivity measurement. For question 2, an ordinary millivoltmeter is not suitable because their inner probe voltage is very small. If the meter has low input impedance, it may draw current from the sample and cause a loading effect. Therefore, a high input impedance electronic millivoltmeter or potentiometer is preferred. For question 3, the energy band gap Eg is determined from the graph of ln rho against 1 over T. The calculation is done using two methods, which are the central method and the least square method. After taking the natural logarithm of the resistivity equation, the equation becomes a straight line equation. Therefore, the gradient of the graph is equal to Eg over 2 kb, and the band gap is calculated using Eg equals to 2 kbm. For increasing temperature using the central method, the gradient obtained is 2232.46 K. By using Eg equals to 2 kbm, the band gap is 0.3847 electron volt. Using the least square method for increasing temperature, the gradient is 2424.57 K. Therefore, the band gap is 0.4179 electron volt. This graph shows a positive trend for increasing temperature. As 1 over T increase, ln rho also increase. This agrees with semiconductor behavior. For decreasing temperature using the central method, the gradient obtained is 2731.50 K. Therefore, the band gap is 0.4707 electron volt. Using the least square method for decreasing temperature, the gradient is 2617.58 K. Therefore, the energy band gap is 0.4603 electron volts. The decreasing temperature graph also shows a positive linear relationship. This supports the expected behavior of a semiconductor. This slide compares the band gap value obtained from the both methods. The values are slightly different because the central method used 2 average points, but the least square method used all data points. From both graphs, resistivity decreased when temperature increased. This is because more charged carriers are terminally excited at higher temperature, so the semiconductor becomes more conductive. For question 4, rho 0 is obtained from the intercept of the ln rho against 1 over t graph. Since the intercept is equal to ln rho 0 can be calculated using rho 0 equals to exponent c. At 0 Kelvin, electrons do not have enough thermal energy to move from the valence band to the conduction band. The valence band is full and the conduction band is empty. Therefore, there are no free charge carriers, so a semiconductor behaves like an insulator at 0 Kelvin.
Now I will talk about the discussion. Experiment M1 entitled Resistivity Measurement of Semiconductors by 4-point probe method aims to measure the electrical resistivity of a semiconductor while minimizing contact resistance for more accurate results. By applying a known current through the outer probes and measuring the voltage across the inner probes, the resistivity can be determined. This experiment also studies how resistivity relates to the intrinsic properties of semiconductors and determine the energy band gap. The 4-point probe method works by placing 4 equally spaced probes on the sample surface. A constant current flows through the outer probes while the voltage is measured across the inner probes. Based on Ohm's law, resistivity is calculated from the measured current and voltage. This method is suitable for semiconductors because their resistivity depends on temperature and impurity concentration. Two formulas are used, which are P equals to P0 exponential Eg divided by 2 kT, which shows resistivity decrease exponentially with temperature. Another formula is P equals to 2 pi s times V over I, which is used to calculate resistivity from experimental values. From the results, voltage decrease as temperature increase. The resistivity decrease as well. This confirms the typical behavior of semiconductor, where higher temperature provides more thermal energy to excite charge carriers and hence increase the conductivity. The consistency between heating and cooling data shows reasonable reliability, although slight difference may occur due to temperature lag or probe contact variations. Now I will analyze the questions. For question 1, the 4-point probe method improves accuracy by separating current supply and voltage measurement. This can minimize contact and lead resistance errors. For question 2, an ordinary millivoltmeter is not suitable because the voltage is very small and low input impedance causes loading effects that may lead to inaccurate readings. Therefore, a high input impedance device is preferred. For question 3, the ln P versus 1 over T graphs shows that ln P increases with 1 over T. This indicates the resistivity decrease with increasing temperature, which agrees with semiconductor behavior. The energy band gap values obtained using the least-square methods, which are 0.4179 and 0.6024 eV, are more consistent than the central method. The obtained Eg values are close to the standard value for germanium, which is 0.66 eV, with some deviation due to experimental errors. Therefore, LSM is more reliable. For question 4, P0 is 6.157 times 10 to the power of negative 5 ohm meter for increasing and 2.0791 times 10 to the power of negative 5 ohm meter for decreasing temperature. At 0 Kelvin, semiconductors behave as insulators because there is no thermal energy to excite electrons into the conduction band. Sources of error in this experiment are poor probe contact, non-uniform sample thickness, and temperature variations. This can affect voltage readings, current distribution, and resistivity values. To improve accuracy, probes should be placed properly. The sample surface should be clean, and temperature should be kept constant throughout the experiment. In conclusion, the 4-point probe experiment successfully demonstrated that the resistivity of the semiconductor decreased with increasing temperature. Typical negative temperature coefficient behavior of semiconductor has been confirmed. The results obtained from both heating and cooling processes provide a more reliable measurement of electrical properties. Overall, the experiment verifies that theoretical relationship between resistivity and temperature and highlights the effectiveness of the technique to accurately characterize semiconductor materials. These are all our reference in this experiment. That's all from us. Thank you.